All right, good afternoon, ladies and gentlemen. Welcome to this pair distinguished lecture series today. Today, we are very lucky to have Professor Joseph Sifakis to give a lecture entitled The Artificial Intelligence and Autonomous Systems. So my name is Qingyan Chen. I am the director of the PolyU Academy for Interdisciplinary Research. We call PAIR. So at the PAIR, as you see just from the video, we have 11 research institutes and 5 research centers focusing on the problems that are of a societal impact, like cities and life science and then also the advanced technologies. So I'm not going to go over all these the details again. So I would like to introduce our Vice President for Research and Innovation, Professor Chris Chow, to give a general introduction of the Polytechnic University. Thank you, Professor Chow.
Hi, thank you, Professor Chen. Good afternoon, ladies and gentlemen. Good morning and good evening to some of you. It gives me great pleasure to welcome you all to this distinguished lecture organized by the PolyU Academy for Interdisciplinary Research, PAIR, of the PolyU. The science fiction action film, I, Robot, released in 2004, portrays how people in the year 2035 rely on robots, which are programmed specifically to help humans and not to harm them in any way. We are now in year 2023, and in fact, a Hong Kong-based company has already developed Sophia, the robot, the first humanoid robot that can show over 60 different human expressions while interpreting human language and emotion. I'm sure that most of us did not anticipate such a rapid AI development 20 years ago. More recently, ChatGPT, the cutting-edge language model developed by OpenAI, has become a worldwide phenomenon. 2 months after its release in November 2022, ChatGPT went viral with more than 100 million users around the world, recorded in January this year, a pace faster than many of the dominant tech companies, apps, and platforms of the past decade. Eminent physicist Stephen Hopkins once said, "Success in creating effective AI could be the biggest event in the history of our civilization, or the worst." Perhaps we should all stop for a moment and focus not only on making our AI better and more successful, but also on the benefit of humanity. The emergence of AI technologies, on one hand, enables task automation, economic growth, and productivity. It, on the other hand, raises concerns about the future of work, cybersecurity, and ethics. Today, we shall gain deeper insights into the AI controversy. Since we are very privileged to have invited our distinguished speaker today, Professor Joseph Sifakis, who will share with us on artificial general intelligence and the directions towards developing an autonomous system capable of performing complex tasks for the mankind. Professor Sifakis was awarded the 2007 Turing Award, which is commonly considered as the Nobel Prize of Computing. I'm sure that PolyU researchers from the Research Institute for Artificial Intelligence of Things, RIAIoT, as well as the Department of Computing, will find Professor Sifakis' lecture particularly useful. A few months ago, PolyU and Hanson Robotics Limited, creator of Sophia the robot, signed a memorandum of understanding to establish the Center for Humanistic Artificial Intelligence and Robotics. RIAIoT will partner with Hanson Robotics to tackle even more ambitious opportunities in humanistic AI and social robotics. Last but not the least, I'm sure that Professor Sifakis' sharing today will definitely be thought-provoking to not only AI specialists, but also each and everyone living in a digital world. I wish the lecture a great success, and I look forward to hearing your active discussion. Thank you very much.
Thank you very much, Professor Chow, for your remark. Now I would like to invite Professor Changwan Chen, the Chair Professor of Visual Computing here in the Department of Computing, to give introduction to our speaker. Professor Chen, please.
Thank you. Thank you, Director Chen, for the introduction, and good afternoon, and maybe good evening, good morning, because I'm pretty sure our audience is worldwide, and so it's common to say everything, good morning, afternoon, and evening. First of all, you see me, my background is different. I wanted to show you that Hong Kong actually have a sunshine and blue sky. So although we are celebrating with the distinguished the speaker today with all red. You know, Joseph, I'm not sure you know, the red is the prime color for China, for Chinese for celebration. So this red color is to honor your speech today. But I want to show a little bit different. So anyway, so it's my great pleasure and also my privilege to introduce our distinguished speaker, Professor Joseph Sifakis, who is, of course, Professor Chow already mentioned. He was the 2007 Turing Award winner, and for his contribution to theory and application of model checking. And I know if you are not computer science, you know, you don't know what this model checking is, which is actually extremely important for many of this software we develop, hardware we develop. Okay, so that's very important. And Professor Sifakis is a senior CNRS researcher, Emeritus at Verimag. And I think that if you don't know anything about Verimag, it's actually probably top institution doing the embedded systems. So building all these light systems with embedded capabilities. And he actually was a director for many years before his retirement. Okay, and of course he also you know, lead many projects in that institution. Okay, currently he has I think he is still working very hard. I know what you know, bring us all these new research directions. And especially is a very important one like AI and autonomous systems. Okay, and he also was a professor before at the EPFL for many years. So he has an industrial background, academia background, and of course research background. So his total is pioneer and also bring the field in computer science forward for many years. Okay. So Joseph told me that not to read all this long bios. If I do that, I'll be talking today instead of him. Okay. So anyway, so I like to just highlight some of this here already, and I like to invite him to start because his talk is much more interesting in my introduction. Thank you.
Okay, thank you for the nice introduction. Can you see my screen?
Yes, it's a
yes. Okay, so I'm really happy to give this talk on artificial intelligence and autonomous systems. And without delay, I would like to start saying that there is currently a lot of confusion about what intelligence is and how it can be achieved. And this confusion is fueled by the media and large technology companies that spread opinions suggesting that human-level AI is only a matter of years away. Also, we know all this mythology that has developed around the issue of ultra-intelligence of machines, and some believe that machine learning and its subsequent development will be enough to meet the intelligence challenge, and this is only a matter of time. Of course, I don't agree with his opinion, and it's enough to look at a dictionary and see a definition of what intelligence is. It's defined as the ability to learn, understand, and think in a logical way about things, and the ability to do this well. So, of course, machines can do impressive things. They perform humans in games, in many specific tasks, and also recently they give an appearance of understanding. But machines cannot surpass humans in situation awareness and adaptation to changes, and this is something I'm going to explain. I consider that autonomous systems is a big step from weak AI to artificial general intelligence. Today we have weak AI that gives us the elements to build intelligent systems, but I don't have the rules to build complex intelligent systems. And this is the challenge of autonomous systems that stem from the need to automate organizations by replacing humans with autonomous agents as it is envisioned by the IoT. There are many examples of this idea: autonomous cars, smart grids, autonomous communication networks. And autonomous systems are distributed systems, real-time systems that are often critical. They should exhibit broad intelligence. They should manage dynamically changing sets of possibly conflicting goals, cope with a certainty of complex cyber-physical environments, and harmoniously collaborate with human agents. I believe that to reach the autonomous systems vision, we need to make two steps. One is to move from automated systems to autonomous agents, leveraging AI techniques, and the other is now how to integrate autonomous agents, and because agents pursue specific goals, and then we should make agents collaborate together and achieve global system goals. What I call emergence of collective intelligence is something I'm going to explain. And of course, autonomous systems integrate AI components, and one problem is the non-explicability of AI, and I hope this is easily understood. Now, this is an outline of my talk. I will discuss the problem of intelligence test, comparing human and machine intelligence. Then I will talk about autonomous systems, and then I will discuss some future work directives. Now, we probably know that Alan Turing, who is the founder of computer science, had the idea to propose this famous test to compare human and machine intelligence. The test goes as follows. You have in two separate rooms a machine and a human. An experimenter C sends questions to A and B and collects the answers. And Turing said that if C cannot tell which is the computer and which is the person, then A and B are equally intelligent. I mention in this test because there is a lot of discussion today about the intelligence of systems, and some people claim that their system successfully passed the Turing test, so it is intelligent. And I don't think that the Turing test is a good test to compare human and machine intelligence for many reasons. And because the success depends on human judgment, you see here, you have a subjective judgment of a human. Also, the choice of the test cases can introduce some bias. I can imagine questions that favor the human or the machine. And finally, the test cannot be just a conversation game, because much of human intelligence is expressed by interaction with the environment. We speak, we move, we exhibit social behavior. So instead, I will propose today another kind of test that I call a replacement test. And this test generalizes Turing test, and also relativizes the concept of intelligence. I would say that an agent A, no matter if it is a machine or human, is as intelligent as an agent B that performed the task if A can successfully replace B. So the task can be any, can be the task of the Turing test, but you can consider other tasks. So I will say that a machine is as intelligent as a human driver if it can successfully replace the driver. Or I will say that a human is as intelligent as a cleaning robot if it can successfully replace the robot according to some given cleaning criteria. And of course, I can apply this to the Turing test, as I said, of course, provided I have a rigorously defined success criteria. Now, another way to compare human and machine intelligence is to consider how knowledge is produced and developed by humans and machines. Probably you know that our thinking combines two systems. Here I'm using Kahneman's terminology from his famous book. Probably you know. We have system one thinking that is fast thinking, that is non-conscious, automatic, effortless. And this is a kind of knowledge we use to walk, to speak, to play an instrument. The system two thinking is slow, conscious, controlled, effortful. And this is the source of any reasoned knowledge. When I write a program, when I solve a problem mentally, I'm using this type of thinking. There is now a remarkable analogy between the two systems of thinking and the two paradigms of computing we have today. We have conventional computers that we program, we write algorithms by using system two, slow thinking. And so this is model-based knowledge. These are models we can analyze, we can understand and verify. And then on the other hand, we have neural networks, and neural networks generate empirical knowledge after training. So this is data-based knowledge, and they can distinguish cats from dogs exactly as kids do. And of course, we have no clue how these networks work. We cannot analyze their behavior, so they cannot be verified. And this is a problem everybody talks about, explainable AI. Now, just to further explain the difference between scientific and technical knowledge and the knowledge produced by neural networks. So this is empirical knowledge, and when you produce empirical knowledge, you have a well-defined process. You do some experiment, then you learn something, and you try to generate some explanation. So here I'm considering a famous experiment in physics. Galileo did the experiments, noticed the proportionality between the force and acceleration, and he formulated the famous law. This is the explanation. Now, if I want to build a neural network that distinguishes cats from dogs, I will have an experimental phase. I will show images to a person that will label the images, and based on these results, or this labeling, I will train the neural network. But the question is, what explains the behavior of the network? What explains the input-output behavior of the network? And this, roughly speaking, is the issue of non-explainability of AI. And now, discussing this comparison between a human and machine intelligence, I would like to emphasize something else that is very important in my eyes, is the fact that humans are equipped with common sense knowledge. Probably you've seen this title in the news: an autopilot mistakes moons for a yellow traffic light. And it's clear that this is never going to happen to a human, because a human perfectly understands that the traffic light cannot be in the sky. So human mind is equipped with common sense knowledge, which is a semantic model, in fact, of the world. It's a vast network that we build progressively. We don't know how. And this is used to interpret sensory information in natural language. What something else that should be emphasized is that we use the network to understand the world, and understanding, in fact, goes bottom up from reasoning to sensor level, and top down from semantic model to perception. And I would like to illustrate this fact by giving an example. If I show you this image here, you easily understand that this is a stop sign, partially covered with snow, just because you can connect the sensory information with a conceptual model you have of the stop sign, with the properties it has, etc. But if you want to train a neural network to recognize stop signs, this should be done for any weather conditions. And this is a big difference between human understanding and learning and neural network learning. And just another example also that I mentioned in a book I have published. You see this sequence of images that is interpreted by a human as an aircraft accident immediately. In contrast, if a machine can analyze each frame separately, identify objects, but cannot create causal relationships between the successive frames and reach the same conclusion. So to summarize, for machines to match human situational awareness, they must be able to progressively develop a model of their environment and in particular to understand the entirely new situations and combine learning and reasoning. And this is the hardest problem I can imagine. This is a core problem in AI today. And of course, I personally am not very optimistic about the possibility to solve this problem in some foreseeable future. Now, let me talk about autonomous systems, because I said that autonomous systems is a step toward artificial general intelligence. And first, I would like to clarify the distinction between automated and autonomous systems. So here I'm considering 5 different types of systems. I hope you understand what they are doing. And all these systems interact with their environment. They should have some situation awareness and make decisions. So for the thermostat and the automated shut, this is very simple. They receive numbers, states of the environment, and their control. They make decisions based on static control. We can enumerate all the control states needed for that. And things become much more difficult for a chess robot, not so much for situational awareness, but for a chess robot, you know that we have an explosive number of moves and configuration of pawns on the board. So here we cannot statically figure out all the possible moves, and we need dynamic planning. And things become much more difficult for the football robot for situation awareness, because now the robot should analyze dynamic images and they have to deal with multiple dynamically changing goals, and things become even worse with autonomous cars. So let me try to give an architectural characterization of the functional behavior of an autonomous agent. And here I'm considering as an example an autopilot. So this is a reactive system, clearly, that continuously interacts with an environment by using sensors and actuators. This is quite standard. How it works, it receives sensory information, say frames, and to achieve situational awareness, understand what happens in its environment, combines 2 functions. Perception function that we usually implement using neural nets, and here you analyze images, you identify obstacles around the car with a very kinematic state, and you build a model. So this reflection function will be the semantic model of the external world. And based on this model, you will make decisions. What means making decisions? 2 things: managing goals, and for each goal, generating plans, and plans are sequences of commands. Now, for autonomous agents, we can have a big variety of goals. Just to mention, for an autopilot of a self-driving car, you can have something between 10 or 15 different goals, short-term goals, keeping the car on a trajectory, avoiding collision, long-term goals. I'm here, I want to go to a destination, and many mid-term goals. So I have to manage these goals, make decisions, resolve conflicts between goals. And this is the reactive part of the behavior of an autonomous agent. But an autonomous agent exhibits also some proactive behavior. And this is based on the use of knowledge. Using knowledge is very, very important to have adaptive behavior. So you see here, I show a knowledge repository where I can have restored knowledge. And also I have this self-learning function, and the self-learning function monitors what happens inside the system and updates the knowledge repository. Why this is useful? Because, for instance, if I am in a self-driving car and I detect ahead of me, so I have an image of a truck in front of me, then if I know what type of truck it is and I have here pre-stored the properties of the truck, I can make predictions knowing that its maximal speed, its maximal acceleration is of this kind. So, particular here, you can use self-learning also to improve the decision-making process, because you can estimate some parameters that intervene in the specification of the goals. So, this is just to understand how an autonomous agent behaves, and this is just a vision. We don't know how to implement autonomous agents like that, because there are a lot of difficulties, a lot of complexity issues, complexity of perception. I hope you understand this. Complexity of uncertainty due to the non-predictability of the physical environment of the agents. You have, or the human environment of the agents, you can have rare events, critical events such as failures and attacks, and also the complexity of the decision-making process, because you have to handle many different goals that are subject to different real-time constraints. So when I modify a goal, I have this modification should be consistent with the other pursued goals. This is a very hard problem. So we don't know how to build agents according to these principles. And what I'd like also to say is that besides building, designing agents, integrating the agents in their physical, in their environment, raises also some systems engineering problems that are not related to the fact that agents are intelligent. And this is surprising because, okay, so this means that building intelligent systems requires also to solve some systems engineering problems. Typically, if I want to integrate my autopilot in a car environment, this is a complex electromechanical system. Also, the autopilot should be able to collaborate with a human operator, and this is not just a human-machine interaction problem. And then if I have agents now, I have to integrate them and to coordinate them in a system. So if I have, say, self-driving cars, they should harmoniously cooperate to achieve other goals. For instance, to have some, not to have the congestion problems, something like that. And this is, so achieving global system goals means that you demonstrate some collective intelligence. So in this slide, I try to explain the difference between agent intelligence and collective intelligence, and show where we are standing today. So being intelligent means that you show some situation awareness and you can make decisions. So as you move in that direction, problems become harder. I hope you understand this. So you can have situation awareness for a single domain or for many domains, and a restricted situational awareness here. And then you can have a system with a single agent or many agents. So let's see where we are standing today. For weak AI, we are here. We have a single goal, single domain. So if you consider, for instance, ChatGPT is single goal, single domain. Now with autonomous systems, we would like to have many goals, possibly multi-domain, and this is it for fixed goals. And the human agent is capable of dealing with a restricted environment, and of course can create goals and manage many different types of goals. Now, when we have agents, we can create systems, and there are different problems here that you have to solve. So you have to integrate the agents and then to make them collaborate to exhibit some collective intelligence. And this is already a goal that is very hard to achieve. And of course, at the top, you have human societies, because humans know how to exhibit social intelligence. If you have questions, I can answer this. So that's where we are here, and that's where we want to go. Okay, so there is a long way, and this is a message. Now, an important question is how to build the trustworthy autonomous systems, systems we trust. So let's talk about how we can build trustworthy automated systems first. We have a very good theory, very good methodologies to build systems that we trust in aircraft, in industrial robots, in nuclear plants. But these systems are developed according to predefined methodologies that are also recommended by standards. Here I show the famous V model, where you have, I'm not going to give details about that, but we have predefined steps. And what is important to understand is that this development flow is model-based. Model-based means that the engineer makes decisions here, and he has to justify his decision by using models. So using models, this is not applicable to AI systems clearly, but using models allows to reach some conclusive evidence that your system, for instance, is safe or is trustworthy. I have applied these flows for avionic systems. So for a flight controller, you have to show that you have no more than 10 to the minus 9 failures per hour of flight. But we can do that because the development is model-based. And this model-based paradigm is defeated by the complexity of autonomous systems and by the fact that you use components that cannot be modeled by mathematical models. So you cannot do that. So what's the situation today? On the one hand, we can build automated systems of guaranteed trustworthiness. We have theory for that. But this is not sufficient. So to overcome this obstacle, some big tech companies for self-driving cars, they have developed solutions that are end-to-end supported by machine learning techniques. So typically, for instance, some companies like Waymo, NVIDIA have developed self-driving platforms, which include a neural network here. They are trained to receive, say, frames from cameras, and at the output we have acceleration, deceleration signals, and steering angle. Now these platforms are available, but I think that nobody can use them because we don't trust them. And also another problem I don't have time to talk about that is very important is that once you have such a platform, you have to integrate it in an environment. And there are standard techniques about how to do that when you understand how the system you integrate works. And because you have to make a failure analysis, a risk analysis, and this we cannot make with this type of system. So there are a lot of problems to be solved. I think that for the future, we should try a compromise. Compromise between, so to find flows that I call hybrid flows, hybrid design flows. So in the same system, we try to integrate model-based components, typically for decision-making. And then you have here neural networks for perception, for optimization problems. Of course, the problem here is how to link model-based knowledge and data-based knowledge. This is a problem I don't know how to solve. And of course, the deployment problem remains completely open. So there is a lot of work to be done to build the autonomous agents. Now, let me talk about the trustworthiness of autonomous systems, because this is becoming a very, very important issue. In particular, we talk about trustworthy AI. More recently, with ChatGPT, we talk about responsible AI, aligned AI, so AI aligned with human norms and values. We talk about honest AI, something like that. So it's very important to provide some evidence that the system meets the desired properties. And what I have explained already is that as we cannot build faithful mathematical models to reason about the systems we build, we cannot apply verification techniques. So the only way to go is to apply testing, to apply some empirical techniques. And this is something I would like to further discuss because this is becoming a very, very important issue. Now, let me say that from a methodological point of view, when you assign a property to a system, you say that my system is honest, for instance, you should define clearly what means honesty, but not like in a dictionary. You should provide validation criteria. You should provide a checking method how to check for the system that is honest. And of course, if you don't do that, this is just a charter and this is not technically relevant. Just to give you some example of what we can find in papers today. For instance, you can read that our system our autopilot systems, our self-driving systems are safe just because we have driven 10 million of autonomous miles in simulation. And this is not an argument that is tenable just because you don't explain how the simulated miles are related to real miles. And you should provide arguments that explain that your simulation deals fairly with all the many different situations a self-driving car can say. Or if you talk about responsible AI, you should provide, and you say that responsible AI means fairness, reliability, whatever, you should provide definitions for these concepts and how this can be checked effectively. And I don't know how to provide such definitions for AI systems. And finally, all the discourse about AI alignment is completely empty and completely hollow. I will not discuss this. If you say that I want my AI system to be aligned to ethical human values, this means that you understand how humans make decisions and act ethically or responsibly, and this is something we don't understand. At least I don't understand. Now, let me discuss from a technical point of view what it means that I can provide evidence that a system S meets a property P. Let me give some elements. So of a rigorous validation approach. So I have a system. So a system is any kind of system. So it can be a physical system, can be the population of Hong Kong, or artifacts like autopilots, AI components. And then the property is a hypothesis about the behavior of the system that is a relation between observers of the system. And the checker, of course, of P, for the property P, can decide logically or experimentally whether P holds for given observer. I do an experiment, I observe something, and the checker will decide. Now, what it means that the system S meets property P? It means that for any possible observable of S, the property P holds is satisfied. And you understand that I can have systems with an infinity of observers or a huge number of observers. So I need a methodology to provide some evidence that S meets P, and I give some elements of this methodology. I don't have time to discuss more of that. But at least you need some framework like that. You have the system. This is a testing framework. You provide test cases, so the test cases are just inputs to the system. The system for each input will produce responses, and the checker now will compare the test case against the response of the system and will give a verdict, success or fail. So this is the setting, the experimental setting. And in order now to be able to say something sensible about the validity of a property P for a system S, you need some theory, and I will give some elements. So the theory should allow to give for a set of test cases, TC, and their success rate, because here I can compute a success rate, to assert that this success rate for a limited number of experiments is the probability that S meets P with a certain confidence level. Without getting into details, you need, in fact, two types of function. A coverage function, that a coverage function for a set of test cases will give the coverage, the degree of coverage of the system behavior. So I hope you understand what is this. In the simplest case, this can be a probability that you explore the system behavior. And then the confidence level functions will give the probability that for a given set of test cases and success rates, the estimated success rate is true for the system. I don't want to get into detail, but well, there are different approaches to do that. But one strong requirement is what we call reproducibility. And this is a very strong requirement every time you are trying to investigate phenomena. You see, in physics, we require reproducibility of the experimental results. And here there is a condition that is a very strong condition that requires that if two sets of test cases have the same coverage, then the success rates are more or less the same and the confidence level is more or less the same. And let me show now applications of these ideas to real systems. So I have here three classes of system. One is okay, this is the solar system and the flight controller. This is so here you have a model of the system, a mathematical model of the system, and you have also everything can be formally defined, and you can check the properties, and you can reason also with the model, and you can get what we call conclusive evidence that the property holds. It's not absolute evidence because it's scientific evidence, but it's the best you can do. And then another approach is to use statistics-based techniques. So here I'm considering populations, and the problem is to estimate, for instance, the efficiency of a medical treatment, for instance, of a vaccine, or you make an opinion poll. And statistics provides some methodology to, provides sampling theory about how to choose the test cases, in fact, to have a good coverage of the key characteristics of the population for the property you want to validate. And this also works. And now I'm considering here two types of intelligence systems. For self-driving systems, you don't have a model of the system, but you can formalize the property. And also you can have checkers. And the problem is how to, is it possible to have sampling theory or this famous coverage function and the elements you have mentioned for testing theory. And for ChatGPT and image classifier, you have no model of the behavior of the system. You cannot describe the property. And of course, the checker is just a human experiment. What I want to say by that, I don't want to say that this is hopeless, but, and also I think that even for systems like ChatGPT, we can develop some theory, but we should restrict ourselves to properties that express relations on the observed system behavior. So we cannot have properties that talk about the intentionality, the beliefs of the system or awareness. This is not possible. And you can talk about the safety of the system if you describe carefully, I mean, give a test benchmark about what it means for the system to be safe. And then, of course, you should, for these properties, you should provide well-founded objective criteria. Now, it's time to conclude about autonomous systems and say that autonomous systems require computational intelligence, but there is also some systems engineering issues. And the traditional systems engineering is currently disrupted by new trends that are driven by the need to have autonomous systems everywhere. You know this. And these are the trends here. So we adopt machine learning techniques, and we cannot guarantee the trustworthiness. In some countries, in the US, for instance, they allow now self-certification, which is, I mean, which means that we don't have standards, and the manufacturer will guarantee the trustworthiness of the artifact they build. So, for instance, Mr. Tesla will guarantee the safety of his cars. And also, we allow regular updates of critical software. You know this, and this is at odds with the standard engineering practice. I think that it's very important that we solve two problems: how to build trustworthy agents. I discussed this issue of hybrid design. Here, the problem is how to introduce in traditional systems engineering flows AI components, and how to build trusted systems out of untrusted components. This is an old problem. We know how to solve this at very high costs for hardware systems, but not for software or AI systems. And of course, this hides another problem I have discussed already, linking symbolic and non-symbolic knowledge. And then system validation is becoming very, very important. We cannot do that by verification. We need testing theory, probably some statistics-based estimation. This means that we will have weaker trustworthiness guarantees than we have for traditional systems, and we have to live with that. I don't know. This is a matter of acceptance of risks. I don't know if intelligent systems will be accepted in critical tasks. So to summarize, to bridge the gap between automation and autonomy, there is a lot to be done still, and I believe that to reach the full autonomy vision, we need to develop a new scientific and engineering foundation, and this will take some time. So now it's time to say something about the future, and I have 3 slides about that. First, what I would like to emphasize is that there is a complementarity between cognitive skills, the cognitive abilities rather, of humans and machines. And this can be used to accelerate the development of knowledge, because humans are limited by cognitive complexity. We know this. Cognitive complexity means that you cannot grasp relations that have more than a certain number of parameters. So, but humans are very strongly developing symbolic knowledge. They can use a powerful abstraction mechanism, and here I give a list of them. But it's a fact that today we have scientific theories that involve only a small number of independent concepts and parameters. Any useful scientific theory in physics, in economics, is a simple theory. And this is due to the fact that we are limited by cognitive complexity. And in some cases, for instance, to make weather predictions, to predict something in economic phenomena, we do oversimplifications that may prove to be unrealistic. And here come another possibility, because machines are capable of computational intelligence by creating knowledge from high-dimensional data. And of course, and their current ability to create and apply symbolic knowledge is limited. But what we can do? We can train AIs with the use of supercomputers to build what I call neural aura. So this will be huge neural networks that we train to predict complex phenomena. For instance, there are some interesting publications about predicting earthquakes. They collect the data from all over the planet, and they train the network with little science, apparently, and they can make predictions of earthquakes, which making predictions in earthquakes with, say, scientific theories is considered a hopeless case. And then, of course, this kind of knowledge will be impossible to apprehend conceptually, and we should think whether how we use this kind of knowledge. But I think that producing scientific and technical knowledge will not be the preserve of humans. And of course, the important question here is whether we will have development of science and technology that will be human-centered and assisted by machines, or there can be a divergence. We will have humans producing some knowledge and machines producing some parallel science and parallel technology. This is a very important question, I think. Now, let me say something else that is very, very important, that because we have to be honest also to understand that our definitions imply something, and if I change the definitions, then of course the discussion takes a different angle of attack. So I have considered autonomous systems that are designed to mimic the behavior of humans that live in physical and social environment. And this gives a human-centric concept of intelligence. But somebody else can define other concepts of intelligence by away from this concept. And it's very easy to see how you can do that. You can consider simpler environments and a limited number of high complexity goals. And I hope this diagram explains what I want to say. So, in fact, being intelligent means that you are able to deal with database knowledge. This is very important for perception. And this is symbolic knowledge that is important for analysis and decision. So you see that humans are very good at that, machines are very good at that. But then you can say that you can change the rules of the game here and say, oh, I will consider a test of intelligence where, so in my replacement test, a human will fail to replace a machine pursuing a single goal, but involving a high complexity, high computational complexity. This, of course, can happen in a game land or in the metaverse. Okay, and an important question is, can we bridge the gap between symbolic and concrete knowledge exclusively by using neural networks? neural models? That's a very important question. There's a big debate about that. So I think that what we see with LLMs opens possibilities. So typically, for instance, if I can decide a property like this, I can, by reasoning, prove, okay, this property for any x pair of p of x, okay. Then perhaps, so this is a problem here, I can tackle it with symbolic knowledge, but then I can perhaps take evaluate this property here for the domain, even if the domain of x is infinite, find some approximation and solve the problem here. So I think that with LLMs there are some possibilities. How far we can go, I don't know. This is probably possible for well-defined language. Now, I think it's very important that we explore the space of possible intelligence that I show here. And in particular, I think it's very important that we understand how human intelligence works. And this is here, there are a lot of questions. And this is what I discussed in my last slide. So by considering human agents as autonomous systems, we understand that there is a key problem that is the relationship between mind and brain, because this is the relationship between symbolic knowledge and the database knowledge. And you understand that mental phenomena are very important to understand what human behavior is, just as you need to understand what your software does, to understand what your computer does. And, that's a very, very important problem. I think that some people have some dogmatic positions about mind. I mean, they prefer working with the brain exclusively, not to address the relationship between brain and mind, because they believe that by studying the brain exclusively, they can understand also mental phenomena and they can penetrate this mystery of consciousness. I don't believe that this is the right approach. And there are many projects that premised a lot in that direction that have failed. Now, in a book I wrote recently, I advocate the need to explore what I call the Big Bang of consciousness. As we spend a lot of money to explore the Big Bang of the universe by mobilizing many teams, a lot of money, perhaps it's important, I believe it's important that we build multidisciplinary teams that have the means to collaborate and explore this problem. And here I give a list of questions that can be a long list of questions. How cognition and language appear through evolution? How do we comprehend by linking phenomena with analogies, metaphors? These are questions that are very important. And how we can ascribe meaning to symbols and things like that. And I hope that someday it will be possible to unravel this mystery of the Big Bang of consciousness. It's one aspect of human intelligence, of course, important aspects. And we will better understand how we act as autonomous systems, that how we act responsibly, how we make decisions, how we exercise our freedom of decision. And this will help us also become better as humans, and this is something very, very important. So thank you for your attention. This is my book that where I discuss extensively some issues I have presented in my talk. Thank you for your attention. Thank you.
Thank you very much, Joseph, for your very comprehensive review of the past work, as well as your prediction of the future. I mean, it's really great, and then we learned quite a lot. And now I think we are going to open the floor for Q&A. So for the audience, you can just type in your question through the Q&A box, and then we'll manage this by reading your questions to Joseph, and he will answer the question. So Professor Chen Changwen, do you want to start with the question? Or you unmute yourself. Please unmute.
Okay, yeah, wonderful talk. Actually, I learned a lot. I think a lot of new stuff since I last talked with you. So it's great. It's great to have this opportunity. I will go back to the very the first few slides you're talking about the Turing test and the replacement test. So I guess I wanted to just to confirm that. So Turing test, since the judgment is by human, so you think that's subjective. And for replacement test, you have a very clear criteria. So you think a replacement test is probably is well defined. Is that correct?
Yes, I mean in any rigorous approach, in science, you need some if you do some test, you need some objective criteria, because if humans decide about the outcome of the test, I mean, this is not science. This is, I mean, you can discuss this in mundane meetings, okay, and you can have quarrels about that. So some people say, I don't know, ChatGPT passed the Turing test. I mean, this is nonsense, technically speaking. And of course, when Turing proposed this test, I mean, he had deeper ideas, but at that time, he could not imagine what the computers would become, okay? And also, you have this asymmetry in the Turing test, because Turing, in his mind, wanted to show that the computers can become as intelligent as humans. But what I explain here is that, first of all, if you say that a system has this property, you should, and you say in physics, for instance, when you say in experimental science, if you say this system has this property, it's not enough to say that the property is to be fair, to be, I don't know, you have also to give at the same time the criterion. If you write a paper, you say, this property, it's not just a definition in the dictionary, it's also, you give the setting, the technical setting, that the experimental setting that you will apply to check this property. Otherwise, it does not make sense in science, okay? So what I try with the replacement test is first to relativize this concept, to generalize at the same time to relativize the concept of intelligence. Relativize in which sense? To say that intelligence is be able to do a certain number of tasks. So let's consider just a task. Humans are able to do a lot of tasks and to combine a lot of tasks. But let's isolate the problem. Just one task. For one task, I give success criteria. So typically, for instance, for autonomous, for self-driving cars, you say, oh, there are success criteria to avoid, here you can apply my test to decide whether a system does as well as a human driver, okay? There are criteria about that. So you relativize, and then you don't privilege, it's a symmetric test. You can compare the intelligence of two humans or two agents in general, okay? And in some cases, this is what I explained at the end of my talk, machines exhibit another kind of intelligence, and perhaps some of our symbolic intelligence can be traded for computational intelligence. So I know how to solve, because I'm smart enough, I know how to solve a problem in Euclidean geometry, I don't know, but then I can take all the possible instances of the problem, train a neural network, and it will solve the problem, okay? So you see, intelligence has at least these two facets, okay? One facet that is, say, computational intelligence, producing database knowledge, and symbolic knowledge, okay?
All right.
Okay, I think I should leave the time for other people. There are a lot of questions.
Okay.
Yeah.
Okay.
All right. There are two related questions. The first one is about the black box problem. When we don't know how machine learning actually learns, according to engineers, appears not the case nowadays, then the neural network are essentially based on a simple calculation. So that's the first question. The second on the complexity of a system. Well, it's a little bit complex sentence here. It's about the number of the steps and the speed to execute the steps. Doesn't make an autonomous one, since it is fundamentally based on simple steps. For example, if then that, at the end of the day, the human behavior is a reaction on the environment and the prior experience. Hence, if then that formula applies, unless we separate the mind from the brain. So I don't know, let's say the question is clear to you.
Okay, let's try to answer the first question. So this issue of explaining, there are papers about.
Yeah, actually, your voice is somehow being cut.
Oh.
Yeah, the first question is the black box problem, right? Because if the machine learning actually doesn't know what the outcome would be, then this neural network essentially is just a simple calculation. Is that right?
No, I cannot follow this. I think that, okay, so what's the question is about understanding. I think explainability is about understanding what the neural network does. So the neural network is a system, we train it, whatever training means, and then we let it go. And the problem you have as an engineer, is that I should find a model, not necessarily a mathematical function, but a model that explains the relationship between input and output, because there is an input and output correspondence. And in fact, this is theoretically possible for some kinds of networks. Because for each network, a network is a structure where you have nodes, and you know that the function computed by each node. I don't want to get into details. So if you don't have a recurrent neural network, so if you don't have loops, you can propagate the inputs and compute theoretically the function that is computed by the network. But this is a too hard problem. It depends on the function computed by each node. But what I would like to have ideally is a characterization. There are papers about that. But this is a very hard problem. And of course, for very complex networks, this is hopeless. But for me, to understand what a network does, as understanding, I mean, there is a very trivial definition of what understanding is, that you build a mental model that you can examine and interpret. And in this sense, AI systems are not understandable.
So in fact, there will be, for the neural network model, you need to train it, right? Then they will be able to let the machine to learn how the model
Yeah.
works.
Yes.
Okay.
Yes, but as a child, he learns how to distinguish between cats and dogs. But you don't understand. So in all the learning functions also of the human brain, we don't understand how this happens. It happens, we don't understand how this happens. The problem, I mean, if you want to build the systems now, this is perhaps an idea we should break. I mean, we should give up. But for the time being, when you build buildings, you build bridges, you build programs for critical systems, you need a model. You have to reason about that and to get convinced that it will work, and to provide some very strong evidence that, for instance, the building will not collapse for centuries, I don't know, or the bridge will not collapse. And you are based on theory, you are based on models. So this is the way we build artifacts today. Now, with AI, perhaps we should change the rules. And that's what suggests some people. In fact, there are papers where they say, oh, we should break with these ideas, we can be less rigorous, and then I don't know. And it is clear that if we try to apply the scientific approach to AI systems, and we don't have models, for sure we don't have models, then we should accept the idea that we take more risks, okay? Or we have only some weak evidence, or I don't know, I mean, how to quantify it. We need some theory about that, and we don't have.
Okay, thank you. Because we have so many questions there, I will just pass the second one and
Okay, so can I ask this on behalf of this different question, not technical question? So the question is, nowadays from schools in Hong Kong and in the world, they are teaching kids computer programming, coding, and so on. Okay, but he believes that a holistic person not just need this hard skills, they also soft skills like communication, manners, empathies, and all these soft skills. So what's your view towards impact of you have such a rising AI on this school education?
Oh, yes, that's a very important question, and that's an ethical issue. I think I did not have time to talk about that. It is clear that any technical innovation has an impact on how we evolve, we humans. So humans have evolved. Remember, I mean, the primitive people, when they built the first tools, they did not need their muscular strength, okay? Or we have machines, we have levers and okay, so any progress in technology has an impact on how we behave and how we develop our skills. If you leave me in a forest, I will not survive, and the primitive man would survive in a forest. Okay, so it's clear that we are losing skills because of progress of science and technology, we had the Industrial Revolution where we've been using machines. Okay, so we did not use our muscular force for that. We don't need it anymore because we have machines. But now we have machines that compete with us with our how we decide, how we reason, etc. And here there is a clear risk. What is the risk? The risk is not that the machines become more intelligent than we are or dominate us because of that. The risk is that we rely too much on machines. And I see children that today do not learn, say, the multiplication table. And because machines can answer to these questions. But this means also they don't understand the concepts of proportionality, of arithmetic, of all this. And this means that the humans will become too much dependent on machines. And this is the risk. Because ChatGPT can write better text than a pupil or a student, okay? So if the student does not make the effort to write good text, this is too bad for humans, okay? And if humans do not exercise their sense of responsibility and their freedom of choice, and they rely too much on machines, this is too bad. This is too bad for humanity, in my opinion. And I think that societies should think about that. Thank you for the question.
All right, thank you. There's a lot of people ask for recording of your lecture because some of them cannot attend. So I just sent out the web link. We'll post Joseph's lecture in the web link. I just post online. That's a practical question for you, Joseph. Let's say for all those piloting of smart vehicles, some think that it's more feasible to focus on level 4 automation, which means driving in well-controlled or geo-fenced environments, and then separate the human driver from AI drivers, instead of the current practice of focusing on level 3, that is the human and the AI drivers mixed environment. And
yes.
The author like to hear your comments.
Yes. Okay, but this is a more technical question. I don't know if all the audience knows all this stuff about self-driving cars. I work, in fact, on self-driving cars, so I can give a very detailed answer. So I think that that's a good question. You know that there is a classification of the different levels of autonomy from 0 to 5. And I don't like this classification proposed by the Society of Automotive Engineers. I think it's misleading because it gives the impression that we can move from automated to autonomous, from other systems to autonomous cars smoothly. And there are many gaps there. So the first the three levels are about ADAS systems, so automation, so the driver is responsible for that. And the other three levels, the autopilot is responsible for that. There is a very interesting level that is level 3 that this person mentions. And in level 3, you should have the autopilot being responsible for driving the car, and you have a human supervisor. This is a very bad idea. Why this is a very bad idea? Because the idea is that the human supervisor can intervene if it is requested to do so by the autopilot, and also that the human can intervene if something goes wrong and stop the autopilot. In both cases, this is we don't know how to make smoothly collaborate humans and machine. This is not a problem of human-machine interaction, because you need a protocol for the transfer of responsibility. You see, for instance, if I am the supervisor and suddenly the autopilot says, oh, I cannot handle this, take over, this means that I have the time, I have the perfect knowledge of what happens to react properly. And this, okay, so the system should communicate to you all the information and make sure that you can manage the situation. And also, another very bad situation is that you may interrupt the autopilot. And in systems we have autopilots, for instance, in avionics systems, this is a very bad idea to stop the autopilot suddenly, because you can have strange behavior. So level 3 is a very bad idea. So I would skip level 3 as noticed by this person. Then we have level 4. Level 4 is, in the future, we will have level 4 autonomy. And level 4 autonomy simplifies a lot the problem of autonomy, because you assume that the self-driving cars have an environment that is predictable in automated highways that are instrumented, etc. So this simplifies the problem of situational awareness. I think in the future we will have, I think there are interesting experiments or level 4 autonomy in China and also in Europe. You can have a car platooning and things like that. So this is autonomy for tomorrow, but we are very, very far from unrestricted autonomy level 5, okay? That is not reachable. I don't even know if this makes sense. Yes, okay, yes.
Thank you. Someone. You mute yourself, someone.
Okay, so I think there are too many questions. I just wanted to pick some of them. It's actually a slightly different perspective. So
yes, but give them one by one, because okay, it's better. And I will try to give a short answer.
Okay, so I think let me see. I think I've seen one interesting. Let me see. Okay, the next one. So I think I'll pick one. There's too many. They are very similar questions. So I don't want to repeat them. Okay. So there is one here. I think on the chat instead of on the question and answer that. It's saying that what you suggest is how can we correlate the neural net models with the different other techniques, for example, control and other things, because I think the person's in so many articles showing that the correlation is 0.5 is good enough. So what do you think of this integration between the neural network with others, how they cooperate? So how closely they should cooperate to make a success?
So it depends what it means, cooperation with what? With
I guess it's integration of neural net with other like control. For example, actually my own research, we have this, for example, we have this flying drone, okay, the UAV, and then the input is visual signals, and then but you need in order to get to this target, you need this visual signal to guide you, but the visual signal is used to control the flying. So do you think that we needed 100% of this integration to get a
well, there are different ways, okay, to integrate, okay. But there are different architectures to do that. One way you can integrate is that you say that you build an end-to-end AI-enabled solution, and then in parallel you run a system that is, I mean, can meet some a certified system. So imagine the solution, the following solution: you have a self-driving platform with neural nets, but then you run in parallel another system that is can avoid collision. It's a simple system. It is certified. Then this means that you run them in parallel. You have a monitor, and the monitor can guess if something goes wrong and passes the control if something goes wrong to the robust system. And okay, so this is the principle of runtime assurance architectures that is now, I mean, this is used in many cases, in avionics in particular. And the idea is that when the AI system will recover because some failures are transient, then you pass back the control. So you can marry conventional systems and AI systems in that manner, okay? I think it makes sense. But of course, the problem here is the transition between, so the transition should be smooth when a system takes over or you pass back the control. I don't know if this person asks this kind of question, but the problem is how to think.
Yeah.
Yes, okay.
Let me read the second part of that. He was the example with image processing during drying of fruit and vegetables. For that kind of integration, I think different system, as you mentioned earlier, the system, if a system has some critical function to perform, for example, autopilot for driving, then you're causing a lot of things. It's different from the other,
it's a different problem.
Other kind of system that you might not need 100%. So essentially, is probably is we need a well-defined the goals and whether or not that goal actually has a catastrophic consequence. If not, we can tolerate it better. Okay, thank you.
Yes. Okay.
But you actually in your slides you already talk about the future, and there's a lot of questions about the future, and I just pick up one. You know, look like at this moment, human cannot be replaced by the AI. But that might change, right? If you look at just how Google reacted with the ChatGPT. So how soon? I mean, the machine learning is so fast. So very soon, maybe we find another scenario, and then we think maybe the AI will really replace us. And according to your experience, how long will it take to have AI replace us?
Yes, but wait a moment. I mean, it's you have this vision of the Internet of Things. So in this vision of the Internet of Things, you should understand that today with the ChatGPT, all this generative AI, they focus on very specific problems and very specific tasks. We should have AI components that are controllers, okay, that drive actions, okay. There are people working on that. And then we should have AI components that can deal with many different goals, okay, and can find compromises between many different goals. And if it depends on what is the vision of AI, what is the vision of AI? It's not clear. What do we mean by artificial general AI? If we mean by artificial general AI to have a super chat GPT and to interact with the human by exchanging tests or documents, etc. This is not the end of the story, in my opinion. Artificial general intelligence means that machines can replace humans in the many functions and their skills. Okay, this is so. It's a matter of definition. If the ambition of the people, I mean, the vision stops in generative AI only, okay, I'm fine with that. I will not discuss. But my vision goes a bit further. And of course, this is supported by the vision of the IoT. We don't talk so much about that, but the Internet of Things. And it's interesting to see that the people today focus on computational intelligence and they neglect systems engineering. But in my opinion, building intelligent system raises also issues in systems engineering. If we don't solve these issues, then we cannot go. You see what happened with self-driving cars. Self-driving cars in 2016, Elon Musk was saying that it's around the corner, okay? And now you have this impressive setback of the industry, okay? So there are hard problems if we don't solve them, if we don't understand, and it's strange, but it's a cultural problem also. The people in these companies, big tech companies, do not even understand the problem, that the intelligence means that it involves systems and software engineering problems, okay? I have an intelligent agent, so what? I would like that to have systems of agents that cooperate smoothly. And this is a problem I've been studying now for years. It's a very hard problem because you will need technology for real-time distributed systems. And whoever understands the problem of real-time distributed systems, you will need some protocols for coordination to exhibit global intelligence. Because if you have selfish agents, and I hope you understand what means selfish agents, I want to fulfill my goals at any price, I don't care about the others. Then you can have global behavior that is not, I mean, or I will say, for humans will not be socially acceptable. You see what I mean, okay? I mean, you can have conjectures, you can have catastrophes, and even if people behave safely from their point of view, okay?
I think that's a very good answer. And of course, a lot of simple work can be replaced by AI already, but the more complex one not. But also, if we go a little bit further, maybe, well, I can ask, can AI has a self-awareness or can have a creativity?
Yes, that's a good question. Yes. So, yes, because of course we should ask also psychologists about that, but because you see, that's a problem. And this is a limitation of the scientific approach, in fact. And this I discovered when I was trying to be rigorous. But there is some limitation. And the limitation comes from the way we understand the scientific truth. You see, can assert as valid only whatever you can observe. So typically you cannot observe, so you observe the behavior of somebody and you say, oh, is he sincere or not? Is he responsible or not? Okay, you cannot, by observing the behavior, and you have this famous Chinese room argument by Peirce. So Chinese room argument shows that a computer without understanding, or an agent without understanding, can exhibit a behavior that shows that he understands Chinese. Okay, I mean this famous. Okay, so if you adopt a strictly scientific approach and you stay what is observable, all you can guarantee is three kinds of properties: safety, nothing wrong happens; security, that you are resilient to attacks; and performance according to KPIs. All the rest, saying that my AI is responsive, or whatever, you can, or my AI understands, you cannot give an objective criterion for that. Now, I understand that this is a problem because, but some people are proposing benchmarks. They say, oh, it is responsive if it passes this benchmark, but this is not, cannot be analyzed scientifically. Okay, so this is a limitation of the scientific approach. Perhaps we should go further. I have no idea, I'm thinking about that. But I want to be honest with that. There is a serious limitation here, yes.
All right, thank you. Yeah, we have actually 55 questions there.
Right.
Yes, okay. We can take some more time. Yes, you can select. We can
So
take,
let me ask you, this question was actually in the chat, and then the pair staff pass on to this question and answer. It's a short question, but I think it might need a long answer, but or maybe a short answer too. So what do you think of the impact of AI, such as ChatGPT, on research community, such as a research paper written by AI and suggestions or experiment from AI? What do you think this impact?
Yes, okay, so let's talk about GPT. Everybody talks about GPT, so it's inevitable that I give my opinion. So no, I think that ChatGPT is really something, is a landmark in the evolution of AI and also in the evolution of whatever we are doing. So I have a lot of respect for the people who did that, and it's a great achievement. Now, we should understand how ChatGPT works. I don't understand all the details, but it is clear that ChatGPT is good at answering broad questions. So if you tell him, summarize the history of China in the 20th century, okay, can give a remarkable, a very good summary. Perhaps, okay, there can be some lack of precision, of coherency, but it can be overall a good summary, okay? Or write a poem, easier, okay. But now if you ask very, very precise questions, okay, then it can be wrong. And I mean, there are papers about that, so no need to comment on that because it reflects the way it builds the text. Okay, so nothing to say more about that. Now, it can have, and this is something I'm thinking about, it can have impressive applications in systems engineering. You see, as an engineer, I had to read books of requirements, I don't know, for satellite systems, 5,000 pages. So now, if I had these books, I would ask GPT to summarize. Perhaps some of the summary would be wrong, but at least it has the capability to analyze the text and find important parts of the text. Or you can give it even a program. You can give it a Java program and say, oh, what do you think about this program? And it can help you understand what does the program. It will not tell all the truth about the program. Perhaps it's not able to tell all the truth, but can be an instrument that in interaction with humans can improve human productivity. I think this is very important. Now, it's very important also that humans are in the loop and the humans be able to judge critically what ChatGPT says. But I think it can be a very useful tool and it will be integrated in workflows for sure. In every services everywhere. But people also should be taught how to work with such tools. Okay, people should be trained how to work, to collaborate with such tools, because also the quality of the answers will depend on the way you ask questions. So if you understand how it works, perhaps, and you know how to formulate questions, you will have answers of good quality. Okay.
Thank you.
There is a lot of research to be done on that. Yes.
Thank you.
All right. Well, thank you very much again, Joseph, for your wonderful talk. I mean, your talk just inspired so many questions that you can see how much people are interested on your talk. So I'd like to thank you for your effort. It's a really great honor to have you as one of our distinguished lecturers. And I also like to use this opportunity to thank all the audience for your questions, no matter where you are from. And we really appreciate that. And I'm sorry some of your questions couldn't be answered because of the limit of time. But we will forward those questions to Joseph, who might be able to have an additional answer somewhere we will post on the internet. So before you go, I would like to make a short announcement. Our next distinguished lecture will be given by Professor Kathleen R. Muller, who is a Vice Provost and Dean of Research from Stanford University. So she was scheduled to give a talk in January, but due to some family issues, she couldn't come. But she will be here in April 12th, and this will be a hybrid mode. So Professor Muller will be here in Hong Kong in person. Then in May, the pair will have the first conference, and this conference is with the topic of research excellence for societal impact, and it will be held from the 8th to 11th of May. And registration will be free, so we welcome all of you to join this conference, and we'll have 16 different topics. And our plenary speaker will be Professor Yan Ning, who is a founding president of the Shenzhen Medical Academy of Research and Translation, and I call SMART. So Professor Yang is very famous in China. She was a former faculty member at Princeton University and now came back to Shenzhen, and her topic will be targeting NAV channels for pain relief, and I think her topic will be very interesting as well. So this will conclude our lecture today, and I thank everyone again for your participation. Thank you.
Thank you. Thank you for inviting.
Thank you very much.
Bye.
Thank you.